All right. So in the last class, in the last lecture, we talked about that how the phase Doppler measurement technique actually works. Wanted to add a little bit of a point over here that when we talked about the fringe spacing, if you look at these two rays, okay, these acts as like two glare points. And when the glare points are close together, the fringes are far apart, which happens in the case of these small particles. When the particle is large, these glare points are further apart, therefore the fringes are actually closer. So that is what happens. And these two glare points, why they actually interfere, that is because if you can think of it like a double slit experiment, a Young's double slit experiment where you have two slits, the two glare points are basically the two sources which are far apart, so they actually interfere and they will give rise to these fringe patterns. Okay, so for the smaller droplets, the fringes are the glare points are close together, therefore the fringes are far apart. And for the larger droplets, the glare points are further apart, so the fringes are very close together. So this is what we mentioned, and we mentioned that because of measuring the velocity bias, we introduced this frequency shift. As a result of that, the fringes were moving. So therefore, in principle, while you could calculate the fringe spacing and infer the diameter of the particle, because these two glare points will lie on the meridional plane or meridional circumference, but in reality you cannot, because that frequency is very high. Therefore, you had to resort to something like what we call here the phase shift between these two detectors. Okay, and we also talked about the selection of the detection angle. So now the time comes that how do you actually realize these phase Doppler techniques? So what are the standard systems and what are the planar systems? What are the dual mode systems? So that is what we are going to do next. So if you look at a standard, I will come where we call this a 3 detector system. Take a very close look at this particular picture over here. So this is a particle. Now, as the particle grows large, the number of fringes between these two detectors becomes, more and more fringes starts to accumulate. Okay, because as you know, if the particles gets large, the fringes are very close spaced together. As a result of that, what happens is that you have what we call a 2 pi ambiguity. Let me try to explain that over here. So this is the particle diameter and this is the phase difference. Okay, so now if you are moving along this line, as the particle diameter increases, the phase difference also increases. This we know from this particular equation already because of the linear relationship, right? The phase difference increases as the particle diameter increases. So it grows and it grows up to 360, and then again it starts from 0. So but you are measuring only a single phase. So your measurement is splitting out this. These have the same phase. Okay. But in reality, so you do not know that whether the particle is of this size or that size or this size or this size, because all of them share the same, phase difference. Because the phase difference has moved up to 360 degree and bang, it again starts. So you populate more number of fringes essentially, okay, in between these two detectors. So you do not know whether you are measuring just delta phi or 2 pi plus delta phi or 3 pi or 4 pi, etc., etc. So there is a ambiguity of 2 pi, as you can see. So you do not know that whether there is a 2 pi, what kind of a 2 pi prefixer you have in front of it. So in essence, your particle diameter could be way off, but there is an ambiguity. For the same phase can be shared by different particle diameters because you do not know whether it is 2 pi, 3 pi, 2 pi and above. Okay, so this leads to a size ambiguity. So as this happens when the particle size increases, the fringes in the far field become smaller and smaller, right? That is what we said, that when the particles becomes larger, the fringes become smaller and smaller, and therefore you get a 2 pi ambiguity. To solve this problem, we introduce a third detector, which is closer to detector 1, for example. So what this detector does is it measures another phase. So it measures the phase. For example, in one detector, the black lines measure the phase difference between 1 and 2. The second detector, this is this dotted line, measures the phase difference between 1 and 3. So this is the third detector. So this measures the phase difference between these two, and then the normal detector, and you measure the phase difference between these two, right? Okay, so what happens now is as follows, that you have these are the same. So this is the ambiguous lines. Now you have this dotted line, which basically represents a second phase difference, right? Now what happens is that, and this grows like this, and this is the maximum particle diameter that you can kind of get, because then you get another ambiguity into the picture. So what happens is that, say you use the first two detectors and you measure a phase right there, right? And then you measure the third detector, okay, which measures the phase like that. Now, so this detector will give rise to a certain diameter, and then you measure the phase difference between the detector 3 and 2, and this will actually give you the particle diameter. So you basically match the two detectors, the readings from the two detectors, and where you think at that diameter, where these two readings are kind of the same, that is the diameter that you choose. Okay? So this is how this thing actually works. So this is how you remove the ambiguity by using a third detector, and then you kind of find out that, okay, for this particular diameter, okay, the third detector is giving me this, and the initial detectors are giving me that. So now you kind of correlate the two and find out that what diameter will actually satisfy these two readings. And that is how you nail the diameter. So for example, over here, okay, you cannot have that, because this detector will give you a different particle size. This detector, if you use this, will give you a different particle size. So this measurement, it cannot be this diameter. It cannot be this diameter either. It cannot be this diameter either, because the phases don't match. Okay, the phases the phases that gives the diameter, that those do not actually match. Okay, so essentially it is the phase difference between the detector 3 and the detector 2 that actually gives you the particle size. So that is a unique function of the particle size. Think about it, that is exactly what it is. Because this is between detector 1 and 3, this is between detector 1 and 2, and this basically, this is a unique function of the particle diameter, the phase difference between detector 3 and 2. That is 3 and 2. Essentially, this is how you nail the system. But remember, there is a maximum limit, again, after which you will have this kind of a problem happening once again. Okay, so so the normal PDPA system comes with a 3 detector assembly, just because of the fact that the fringes in the far field become smaller and smaller, and you get this 2 pi ambiguity where you are not sure that what is your particle diameter by just measuring the phase, because there is a 2 pi 2 pi add-on onto the top of it. All right, so this is how you do it. This is for example a spray nozzle, and this is again the two laser beams frequency shifted, they merge at this particular point, you create that. So this is basically the detectors, and this is basically the third detector as we saw, and this is how you correlate the two diameter by looking at the two phase shifts. And then what happens is that this may be segmented lenses actually. So the segmented lenses actually focus it on 3 photodetectors, okay? And from the photodetectors, you get this, this Doppler bursts, essentially. These signals are the same signals that we saw earlier. Let me just pull up that example. This is the same as this, what you saw, okay? So this is exactly those signals that you see over there. And this is how you actually do it, and this is how this entire system actually looks like. So these are the different detectors, and all the detectors are housed. It can be also focused on multimode fibers, and then go to a detector unit. So you have again composite lenses which focuses the beams at different slits. It passes through different slits and then it kind of goes into the detector unit, and then you do signal processing and you do all these things in the software at the background. So this is how this thing actually happens, to be clear. Okay. Now, since this can be done, why not do what we call a planar phase Doppler system? So the same measurement principle can be realized if the detectors are now placed in the same plane as the intersection of the beam. Okay, so you are basically here. One detector is here, one detector is here. So they are actually in the same plane, but at two different scattering angles. So the detectors have two different scattering angles, but they have the same elevation, which is basically a null elevation. So instead of going down the meridional circumference of a particle, you go along the equatorial circumference. You go along this equator, and you can also go through this meridional. It depends on when the detectors are stacked at an elevation. That means this detector and this detector are elevated. You go along the glare points along the meridional circumference. But in this particular case, you go for detection along the, the equatorial circumference. Okay, so these are what the two detectors are doing. They are at angles of psi1 and psi2 from the major optical axis. So this is what you are going to get. Okay, so this is the planar Doppler. So the elevation is null, and therefore the glare points lies on the equatorial circumference rather than here, which was the meridional. All right. Other than that, there is not much of a difference between these two. All right. So now if you look at it, in a dual mode Doppler system, so you basically combine best aspects of both. You combine a standard Doppler phase systems where you have the two detectors U1 and U2 at certain elevation. Okay, so this is the elevation angle, like what we did, and this is the standard U1 and U2 Doppler burst. So these two velocity components are available and two size measures. Okay, because of this, and and then you have the planar measurement. Okay, where you again get these two signals. This is between V1 and V2 now, which are placed at the same plane with no elevation, and these two are at two elevated locations, okay, away from this particular plane. U1 and U2, V1 and V2 are in the same plane, so they will also give rise to this kind of a Doppler burst. So in effect, what you are doing is that using the standard Doppler, you are measuring the droplet size, doing along the meridional circumference, because it will give you two size information now. One will be the size information using the meridional circumference. The other will be the size information along the equatorial circumference, right? And then there will be two velocity components that will be available as well using these two detector assemblies. Okay, so the idea is, why do we do that? We will come across to the next slide, why we actually perform this kind of a measurement. So you understand that, this corresponds to meridional, green corresponds to meridional, blue corresponds to equatorial, and these two detectors are placed at an elevation. V1 and V2 are placed in the same plane. So this is the thing that you should keep in mind when you are actually doing this measurement. Okay, so the dual mode phase Doppler has got therefore a sphericity validation. So what does it do? It takes measurements, because you have particles basically, or droplets, which are mostly spherical, but some of them may not be spherical to begin with. And remember, we need spherical particles to use the equations that what we did. So in essence, what we do is that you measure the droplet size using the meridional circumference, and you measure the droplet size using the equatorial circumference, right? Okay, so this is basically the standard phase difference using a standard Doppler. This is the phase difference using the planar Doppler. So what happens is that if both of them gives rise to the same size, or basically the same phase, that means the droplet is spherical, because for a droplet this and this does not make any difference at all. So you should ideally have a line and the droplet diameter will fall right on the top of it. Okay, all right. But if it is a non-spherical, what will happen is that the standard phase Doppler, because it is non-spherical, means it's probably elongated along one of the sides, one of the meridional circumference or the equatorial circumference, depending on whether it is elliptical or whether it is something else. Like, for example, I will just give this example over here. Like, it can be like this. Okay, that can be one thing, or it can be the other way around, like that. Okay? So both of these two things are possible. So then it will not lie in this particular line, because they won't give you the same phase difference. As a result of that, it will lie somewhere else. The moment it lies somewhere else, you have to reject that particular measurement, because those are non-spherical. So in a typical experiment, there can be spherical particles, there can be non-spherical particles as well. Now, when they are non-spherical particles, you have to some way reject those non-spherical particles. Okay, so typically it is not just a line, you have a band around it, which is basically a threshold. That means you allow a degree of sphericity, okay, maybe 90%. Okay, so that means this too, well, this can be like considered to be roughly spherical. No, this is not exactly spherical. Okay, that I tune it a little bit. So this is not, this is a little bit elongated, for example, but it is kind of spherical, so we can live with it. So these bands are therefore basically for that, to allow for a certain margin, certain threshold. But if it lies away from that threshold, okay, you reject that particular measurement, because the sphericity validation is not done, because you have two different phase Doppler phase measurements coming from the two detectors arrays, one in plane and one in the elevation. So you have to reject when your meridional and your meridional and your equatorial circumference measurements do not align. Basically, the glare points do not align with respect to each other. Okay. So this is, for example, particles which, if the particle is 0.7, okay, whether you accept it or not, okay, so it probably will be rejected. So this can be used for this sphericity validation. So some of the equipments do have that, because that actually pollutes your measurements, so to say. So this is, for example, from Nicholas Appel, who has been our collaborator in the Indo-German Science and Technology Center project. And this is on supersonic closed-coupled atomization. Now, well, closed-coupled atomization is something that we can talk about later, but because that is not the subject over here, this is basically a supersonic, flow interacting with water in this case, which gives rise to droplets of varieties of diameters. And because the flow rate is high and the atomization characteristic is pretty catastrophic, you get droplets which are of different sizes. Some of them may be even ligaments, for example. So they are not spherical at all. But all of these will actually scatter light, and they should actually give rise to a phase difference, and they would spit out. So if you are doing it across the meridional circumference, that is not good enough, because that will give you a measurement which is not correct. So as a result of that, you can see that these are the lines once again, and you can see that this is 1/3 phase, for example, you see that all the particles, I mean, this is size, so it has got a varieties of size, by the way. It is not one size, so therefore it gives rise to several phases, and you get the different, different phases and different particle sizes and all these things. Okay, but this is basically the phase difference between the planar system and the, the standard system. This is standard, this is planar. That is what we talked about. So all these phase differences, correspond to different types of particle diameters. As you can see, you have a band. So most of the, about I think 90% plus measurements actually fall within this green band, and the red ones are the ones which are basically rejected because they fail the sphericity test. So, though it looks like a lot, but actually there is a lot more particles in that range. So most of the particles, or droplets in this case, are spherical. Only few of them are actually, or a few percentage of them basically lie outside the threshold. So this is basically the phase, the spherical validation with dual mode phase Doppler measurement that we can see over here. All right. So that is what the key thing is. Okay. Now you also use what we call filters, spatial filters. Okay. And we will see why we do that. For example, this is with no spatial filter. This is with a slit filter. This is another slit. This is a slit which is being placed horizontal. So this spatial filter is placed in the receiving part. So when you actually receive the beam or receive the light from that measurement volume, before you focus it, on your fiber optics or your photomultipliers, you use a spatial filter in the path. So this spatial filter can be like no filter at all, or it can have slit of different kinds, and then it can even have a pinhole. So all these filters are routinely used, and this is the spatial filter selector. Okay, so and then you have the segmented lens, which basically kind of focuses it on different multimode fibers. So these are for V1 and V2 and U1 and U2 roughly. So the spatial filters, spatial filters are regularly used for phase Doppler receiving optics portion. So this is, for example, the filters. This is mask A, mask B, mask. So all these different types of dual mode. This is written in German, so but these are masks. The interchangeable detection mask for the 3 detector and dual mode system allows you to change the measurement range and resolution. So you can change the resolution by controlling how much light actually enters, and this enables you to change the measurement range and the resolution both by using masks and filters. Okay, so that is what you use, and these are of different kinds, as you see. Okay? Different types of masks, different types of configuration. Okay, so the aperture shape also kind of matters. So in this particular case, for example, this is the influence of the detection aperture size on the linearity of the diameter and phase difference relationship. So this is, for example, the phase difference phi 1, 2, and this is the particle diameter. Okay, this is a point detector, and this is a rectangular aperture, as you can see, and these are from the Lorentz-Mean theory. So as you can see that you want a linear relationship because you are doing a calibration-free measurement. So the particle diameter and the phase difference should be very unique. I mean, there should be no nonlinearity coming into the picture. So this is for point detector system, and this is using rectangular apertures. Okay, and this is measured up to a very large diameter particles that you can see here. Okay, this is also the same plot. That means how the spherical validation was done by Nicholas Appel. Okay, so for highly focused measurement volumes, example high density sprays, the slit effect, okay, can lead to incorrect measurement sizes, correct size measurements. This is also something that you should note. So the detection volume, the projection of the slit aperture for highly focused measurement volumes, high density sprays, for example, you have to do that, and the slit effect can lead to incorrect measurement. Okay, so we also need to recognize, I mean, these parts you can read up separately. So these are, for example, the recognition of the Gaussian beam and the slit effect. Okay, so these are measurement points from pure reflection. Okay, these are measurements from pure refraction over here. Okay, and this is symmetric receiver mask. The measurements from pure refraction is validated. This is not validated, by the way, and this is measurements from pure reflection validated. So so this is how you take the measurements. Now we do a little bit of what we call the signal processing. In the signal processing, what we have is that from the 2 Doppler signals, the velocity, the frequency is related to the velocity, and the phase difference is related to the size. So the 2 approaches are commonly used. One is called the cross-spectral density, and the other is called the cross-correlation. So you will see what that is. So the cross-spectral density function is computed using the Fourier transform of the individual signals. You do the Fourier transform of the individual signals, then what you do, you define something which is called the coherence function, which is nothing but the conjugate of the x, one signal, with the y. So the coherence function, what it does, it indicates the distribution of power or power distribution of signals in phase with one another. So the quadrature function, on the other hand, the quadrature function for signals which are out of phase. So what happens is that if the signal is completely in phase, all the power will be contained in the C, and if all the signals are out of phase, then all the power will be there in the quadrature function. So the coherence function will actually, so the cross-spectral density function is this. The coherence function will contain the functions which are in phase, and this will have the out of phase. So basically, if you take the tangent of the angle between the the complex plane between the quadrature and the coherence function, the theta that you will get, is the one that indicates that what is the power kind of distribution between the two. Okay, so in other words, what we do over here, this is signal 1, that is x. This is signal y. As you can see that they have their amplitudes. Then there is a phase difference. So the cross-spectral density is therefore an imaginary function, which contains a real part, which is the coherence, and an imaginary part, which is the quadrature function. Okay, so the coherence function actually relates to, more the two signals are in phase, the coherence function will grow, and the quadrature function will grow if they are out of phase. So this is in the complex plane. Okay, and you realize that why they are complex. So the coherence function therefore indicates the power distribution. The magnitude and the phase of this is therefore given by that. Okay, so this is how you process the signal. So you convert these signals. First you take an FFT, you convert that into the Fourier space, and then you multiply the signals. Basically you take the conjugate and multiply it with the other one, and then you get what we call the cross-spectral density, which is now composed of a real part and an imaginary part. The real part is basically comes from the coherence function, and the imaginary part comes from the quadrature function. Okay, and this is what it is. So in phase, all will be in the coherence. Out of phase, completely will be there in the quadrature function. So that is how you basically process the signal. So what happens after the signal processing is done, okay, you will get, this is your overall, the cross-spectral density, and this is the argument. Now you will see that this power is more or less at a particular frequency. This is the frequency, and then you calculate that what is the kind of phase for that particular power. So the phase that you get, okay, so this phase, for example, here comes out to be around 86 degrees, and this is what you use to calculate the droplet diameter. The others are, you can see, they are sporadic. I mean, they are all in the noise level, but here, of course, you can use some kind of a signal fit also, but this is the principal signal, and this is what you get for here. Okay, so this basically, so the frequency signal is found at the peak position of this particular spectrum. So the phase difference is given by the theta xy, which is basically nothing but this. That theta xy is at that frequency. You will see that this is about 86. So this is at the peak. At the peak, whatever is your theta xy, that is what you are going to find out. So, so that is how this particular signal processing part actually works. So in the next lecture, we are going to look at a few examples, but this is where we end the signal processing part of the PDPA.